Oké, dat ziet er ook goed uit hier. Ja, moet hier het geluid even uitzetten. Hoor ik iets van het geluid? Ja, natuurlijk hoor ik wat. Dan ga ik naar de kant. Oké, dat zit beter. Dat zit ook beter. Okay, welcome class. Welcome to the continuation of the course on Multibody Dynamics B. We're now at lecture number 9, and the topic of today is a Newton-Euler equation of motion for a rigid body in space. So what we now do is, the first part of the lectures we demonstrated all our methods in a two-dimensional space, two-dimensional examples. However, now we want to make one step further. We want to go out into space at one dimension. Now you would think from 2D to 3D is only one number, but it seems in complexity to be like complexity of 2 going to a complexity of 6, something like that. It's suddenly becoming very complex, and that has to do with orientation. So the coming lectures, I think the coming 3 lectures, we will focus on how to represent orientation, how to calculate that, what are the equations of motion for orientation. But of course, before we do that, we have to do, Kahoot, right? So the Kahoot quiz. Okay, so let me see, where is my Kahoot? Yeah, where are thou, Kahoot? Come on. Okay, in-class quiz number 9 for this year. I don't understand this screen, but we are classics, right? Yeah. Okay, we see the number. Yeah, I see that in the live stream 105 people are watching. So I expect a little bit 106 plus numbers. So I see 111. So let's start the quiz. Again, 5 questions. First question. And that's about, again, the number of cuts you have to make in order to make an open loop structure of such a system and analyze it. I made all the questions on purpose, 90 seconds. Some may need less time, but I did it mainly because of the live stream we have and the delay in the live stream, which is on average 10 seconds, but still it depends on where you are. So be aware of these 10 seconds. Okay, yeah, great. So the majority is correct. Some of you think 2 cuts, so let me look again at the problem, and I have a hunch why those think it's 2 cuts. You would think, oh, if I make a cut here in 2 directions, then I have 2 open loop structures, but this is a slider, and it's still constrained to this surface, so you also have to cut it here. So finally you have 3 cuts. Very good. Oh, very good. Non-Nonallen constraint equation is, so look closely at the figure. We have here a rigid body with a skate, so one rigid body with a skate at A, and the velocities are Vx and Vy at the center of mass, and the orientation is phi, and omega, or W is the angular speed. And the big question is, what is exactly the non-holonomic constraint in A such that there is no lateral velocity? And take your time, scribble on a piece of paper, write down what the speed of point A is, and you'll find the correct answer being one of these four colors. Yeah, very good. So majority is correct. Some of you think it's the answer from last year, but of course I changed a little bit in the assignment. This is about the magnitude of the Lagrangian multiplier. So we add a non-holonomic constraint in a zero-terminated thing. We add that to the virtual power expression, and then we add it by means of a Lagrangian multiplier. And then the question is, what is the physical interpretation of the Lagrangian multiplier? In this case, I say the magnitude. By the way, this is only 60 seconds because, well, sort of easy, right? Not very rocket science question. Yes, indeed, it's of course a constraint force. Okay, next one. Euler equation of motion for 3D rotational motions are. So you see one rigid body with an angular speed, an applied torque, a mass moment of inertia matrix, a capital I, and an angular momentum vector h. And then the big question is, what are the Euler equation of motion for this body? Of course, you can use external sources or discuss with your colleagues. You can look it up in the book or on internet. There are a number of sources available. Or maybe some of you just know it by head. I always have trouble remembering the signs. But then again, using my physical intuition, I think, this must be the correct answer. Seems like a difficult one. What is this? Yeah. Indeed, a difficult question. Now, I don't have to show the media, right, to discuss the answer because, well, we know what it's about. The majority is wrong. So the majority, the blue or the purple, whatever, think this is the correct answer. Well, the first part is right, but the second part, the order is wrong. And it's not the angular momentum cross product with omega, but it's omega times the cross product with omega times the angular momentum. So that's what I mean with the signs, getting the signs right. And why is that? Well, because you have this transport theorem, and it says if you want to look at the change in a moving system, then you have to always add omega cross the thing you do. So please look up the chapter on transport theorem, which is in the book in the first part, and that will enlighten maybe a little bit. Okay. Oh, we're already at the last question. That's when you're having fun, right? Here we see a remote control. It has 3 distinct mass moment of inertias, and there's an order. X is smaller than Y is smaller than Z. And then the question is what the unstable torque free rotation is possible about which axis? It's getting better. Indeed, it is the intermediate axis about which the rotation is unstable. Why? Well, the answer will be at the end of the lecture, where I will do an example, and I will show that it's the intermediate axis. Okay, then we're finished with this. We have a podium. That's good. Congratulations to number 5120322. Get feedback, that's always nice. Save the results, direct download. And to be sure to save it in my drive, it's always nice to have it there. Okay. Yeah, and then we can see the feedback. No, that's something different. Okay, well, whatever. Yeah, I kill that for now. I'm happy with that. I leave the site. Yes, and I'm back at my presentation. Okay, so much for the Kahoot. Now we move on to the topic of today. Bedroom. So, Newton-Euler equations of motion for a 3D rigid body. And in the book it's chapter 18, and I think the title there is a bit different, like going from 2D to 3D or something like that. So, Newton-Euler equation. What do we see? Newton, well, we already saw that, and Euler, we already saw a little bit of Euler equation of motion, but now we want to go from a 2-dimensional body to a 3-dimensional body. And to do that, let's see what the case was in the 2-dimensional case. So in the 2-dimensional case we had 2 axes, right? And in this case the first part, the Newton part, is actually super simple, because we had like a blob here, a mass, and we have 2 directions here, x and y. And then the idea was, well, the Newton equation are the sum of the force in the x direction is mass times x double dot, and the sum of the forces in the y direction is my double dot. So that is the Newton part in the 2D. Then the Euler part in the 2D, well, the Euler part is suddenly about rigid bodies. So now instead of a point mass, we have to draw a potato. So I draw a potato here, and in the potato we have a center of mass. We will come back to that, what that exactly is. And then on the potato is some marker line, which gives the orientation with respect to the horizontal line. So again, x and y, but now suddenly we have this orientation, phi, because it's a body with an extension. And then of course we can apply for all these pieces of small mass dm at the distance r, we can apply our Newton equation and then sum everything up. And if we do that, then finally the equation we get is that the sum of the torques at the cm, so let's say cm here, equals, and then we say that's the mass moment of inertia at the cm times phi double dot. Now of course it doesn't tell you anything as long as you don't know what is ICM, and then ICM is defined as follow. It's the integral over the volume of the distance of a particle with respect to that center of mass. So that I should do a bar on that because it's the relative distance, is this r with a bar, times the mass dm. And that just integrated over the whole body, all these relative distances. So the vector r is x bar, y bar. And that is the mass moment of inertia by definition. The units are, of course, this is kilograms and this is meter squared, so kilogram meter squared. And you could say it's how many mass I feel at the distance. Okay, so that was simple, that was the 2D case. Now we go to a three-dimensional case. Well, the Newton part is actually super simple, right? We just have one more axis, and we still have a blob here with a mass m, and we just extend our equation with one. We say sum of the mass times x double dot, sum of the forces in the y is a mass times y double dot, and the sum of the forces in the z direction is mass times z double dot. Okay, but now we get to this rigid body, and this rigid body suddenly has an extension, right? So it's a real potato with some dimensions. Torques are applied to the body. What else can we have? Yeah, we have of course an angular speed, and now there's not only one angular speed, because in this case there was only one angle and about the vertical axis, so there was one angular speed. But now in the three-dimensional world, x, y, z, we not only have rotation about the z-axis, but we also have rotation about the x-axis and the y-axis. So in general there is an angular speed vector. So I'll draw it something like this, angular speed. Then what does the Euler equation look like? Well, again, of course, sum of the torques. It's now a 3D vector. And again, mass moments of inertia. But note, this is now a 3×3 matrix. Times the angular acceleration. And you will think, okay, we're done. Well, you're not. There's this convective term, omega cross, and then I dot omega. Yeah, the dot is a bit confusing. I shouldn't write the dot. It's just matrix times vector omega. This is what we call, yeah, the convective part. And today we're gonna find out the structure of this. How do we get these terms? What is in here? That's the lid we're gonna open. And this is all known knowledge, and this is actually the new knowledge for now. Okay, all systems are still go, that's good. So let's focus on how did we get this Euler equation, this strange nonlinear term. Now to do that, we first have to get back to this one. Does anybody remember how we got up to this invariant quantity? Well, invariant with respect to accelerations. And for that, if you don't remember, we just have to go through the analysis. And the analysis goes like this. We take some rigid body, and we have some coordinate system, right? And I assume that it's at the center of mass. Now it's a strange picture because the center of mass couldn't be here, but well, for Pete's sake, I need space. So then I have coordinates here, x and y. And then what I'm going to do, I want to write down, and maybe I put a prime here to denote that it's with respect to the center of mass, because here I have my inertial system xy, which is sort of inertial system. But here locally on the center of mass, and maybe I also put this in it, that you know, oh yeah, that's the center of mass. Locally within the center of mass, I measure with x prime and y prime. And then I can take a particle, and a blob, and we call this usually dmi from particle I, and it has the position vector, of course, xi prime and yi prime, this particle I. And then of course such a particle can also have an acceleration x double dot I and y double dot I. So we have a little particle which has accelerations and it has mass, and we can find the particle by in the rigid body moving over these distances, by the way, which are invariant within the rigid body, because it's rigid, so this doesn't change. Now it changes because I scale it, but you cannot do it for a rigid body. Okay, then so this is the kinematics part, and then of course for that same body I want to look at the forces. So again I have to draw the body. I could copy it, but for now this is okay. I draw again my coordinate system with my x prime, y prime at the CM, and I have again this piece of mass dmi, and again we have this distance x prime I and the distance y prime I, and now I'm going to look at the forces, and I say on this force, this small particle, I have a force which I call dF inertia in the x direction and dF inertia in the y direction. Why dF? Well, because this is a small piece of mass, dm, so I have a small contribution to the inertia, the D'Alembert type of forces. Now, how did that work with the D'Alembert forces? Remember, what did D'Alembert say? Well, F inertia, and that can be a vector, right, is minus the mass times x double dot. And why did he do that? Well, then from a dynamics problem, sum of the forces is mass times acceleration. He can make a static problem, sum of the applied forces, this is applied, plus inertia forces is then 0. So then from a dynamic thing you make a static thing. They sort of like that. Well, I like that to illustrate what we're doing. So now this is about forces, but what we actually want to know is of course not the forces, but we want to know the torques. So what torques do these inertia forces give? So we need to know an inertia torque. So what is the inertia torque? And if we have that, then finally we can write down what is the equation for the rotational motion. So we have to look what are the contributions of these forces to the torque about this center, and we take this as a positive rotation. Then and therefore also all the torques will be positive. So we also have a dmi here, and the dmi is a result of these forces. Now how does that go? A little bit more space, yeah. So the dmi, the inertia torque, is of course, well, it's this force, the x times the y, and then with a minus, right? Or let's start with the fy, it's okay. So xi times df inertia in the y direction, minus the other one, so this is the plus, and this one gives the minus, the y direction by the inertia force in the x direction. Okay, and if we want to then know the whole inertia torque, right? What did I say? Yeah, the whole inertia torque. then what is that? That is the sum, of course, of all this stuff. And that of course is then finally our expression for this I cm times phi double dot, right? So that's what we are seeking. Okay, so we know the force expressions, we know that. Then we have to find out what are the accelerations in the x direction and the y direction in such a rigid body as a function of the accelerations of the center of mass. And because the center of mass has velocities, has accelerations, has angular velocities and angular accelerations, and all these will contribute to these linear accelerations in x and y. So we have to find out what the kinematics is. To do that, of course, we draw again our strange blob rigid body. We draw our coordinate system, and that was the so then we take this piece of mass again, this dmi, and now we have to write down what are exactly all these accelerations. So this is x prime, this is a y prime. So let's put the distance. This is x prime I, and this is the distance y prime I. Then I presume, of course, that the center of mass, this guy, has some speeds and some acceleration. So it has a position x, y, and phi. It has a, with respect to this inertial system, x, y, and phi. It has, of course, speeds, x dot, y dot, phi dot, and it has accelerations, x double dot, y double dot, and phi double dot, all at the center of mass. And then the question is, what are these accelerations? Well, first of all, this is just a linear part here, so we can add everything to that. So now let's look at the relative motion. So the motion due to, and that is, of course, the rotations, right? So forget about the linear part for now. We're now only focusing on this rotational part. And the linear part we just make up because we just add them to them. So the rotational part. So maybe it's good to put the rotation in. Fine. Then what do we get? Well, if we first take the angular acceleration, then if we have an angular acceleration about this axis, then of course this part, the angular acceleration in the upward direction, will be this distance times this. So that's x, y prime times phi double dot. Likewise, in that direction, we have an acceleration, which has to do with this distance. So that's y prime I times phi double dot. Then, of course, we have this centrifugal acceleration due to the angular speed. And again, that has two components. And it has a downward component here, which is, of course, phi dot squared times this distance. Y, that's not a nice y. Oopla, go back. Phi dot squared times y prime I, this distance, and in this direction, because the centrifugal is always directed in this direction to the center, that's phi dot squared, and then the distance is x prime I. So, from the picture we now can conclude that the acceleration of point I is first of all the acceleration of this part, of the cm, so x double dot cm, and y double dot I in this part is of course also y double dot cm. And then we have to add all these contributions. Well, let's start with the centrifugal part, so that's minus this one and minus this one, because that's always directed towards the center, so that's simple. And now we have to take care of the signs, because one with the angular acceleration is positive and the other one is negative. So in the x direction we get a negative contribution, minus yi phi double dot, and in the y direction we have a positive with the xi phi double dot. Okay, so putting in these accelerations now into our equation here for the inertia forces, and then multiplying with the different distances, we finally find our torque. Yeah, remember? So we had our expression. Don't become smaller. We had our expression dm inertia I equals, well, it was this distance xi times the df inertia in the y direction minus, we see that minus sign again, df inertia in the x direction. And these inertia forces are, of course, the dm times this acceleration. So finally we get that the dmi inertia at particle I equals, now big bracket, xi times, and now we have to take this in the y direction the inertia force, so we have to take this guy, so y double dot cm minus y prime I phi dot squared plus xi phi double dot, yeah. And then the next part is minus this guy, and again there's a prime, of course, times, and then we get the x direction, the inertia force in the x direction, so all these accelerations in the x direction, x double dot cm minus x prime I phi dot squared minus y phi double dot. I tend to forget some primes now and then, but in the book everything is jiffy and clear. Okay, and then times, shift a little bit, times dmi, of course, mass times acceleration times distance is torque. Okay, now let's see. It seems pretty complex, but you will see it will get simpler and simpler. Well, first of all, we notice that we have a term x times y phi dot squared, and we have y times x phi dot squared, and one is a plus and the other is a minus. So these cancel out. Plus, minus, so they're gone, right? So this term is gone versus this one. I shouldn't put this here. This should go away. Yeah. So because of the pluses and the minuses here, this is it goes away. And that's sort of logical, because the centrifugal force is always directed towards the center, so it will never give a contribution to the torques. Okay, now the other parts. So we are stuck with this guy and with this guy. Now what is going on with this guy? So we have the integral of x prime I y double dot cm dmi. And I say that is by definition 0. Yeah, because the COM is defined as that the integral of distance times mass is 0. And since we have only this constant acceleration here, you can pull that out of the integral and you remain with distance times mass. And the distance times mass integrated over the thing is 0 if x prime I is the distance with respect to the center of mass. So because of the center of mass definition, this is always 0. Likewise, of course, the other term, what is it, the y prime I x double dot cm dmi is also, of course, by definition 0 because of the COM definition. Integral y prime dmi is 0. Static moment should be 0. So that is clear. Then the only thing which remains is this term and this term. And then we see that the dma inertia I equals x prime I squared plus yi prime squared times dmi. Ergo, our inertia torque is then the integral of this stuff, and that is by definition this ICM times phi double dot. Oh, I forgot the phi double dot here, sorry. And then so we see that the ICM is then integral x prime I squared plus yi squared prime times dmi over the volume. And here we saw a nice derivation of what is mass moments of inertia. Okay. Yeah, phi double dot. Then next step. yeah, what is the next step? The next step is, of course, that we now have to move from our two-dimensional body to the three-dimensional body. Okay. And bear with me, it's going to be a little bit more complex, and I need your imagination, because now I'm going to draw a figure on a flat screen, and I hope you see a three-dimensional thing in it. So we start first with a inertial system. And we went to a big trouble in the book to be clear about frames and reference with reference to what. So we talk about a frame, and the frame usually has a curly letter. And in this case, the frame is what we call N, and the frame is the inertial frame. You would think inertial, why not call it I? Well, I is the identity or mass moment of inertia, and I, that is me, and well, whatever. So inertial, we start with the first medeklinker, not vowel, but well, the other thing. So the N for inertial frame. Of course, you can also call it bicycle bell, but we call it inertial frame, N. And then we have the origin, which we usually call O. So this is a fixed in space, and maybe if you like it on top, you can say, oh yeah, this is really the fixed world, right? Because, well, in it, the world is of course not fixed, we're floating in space, but for our small problems here on Earth, we can assume that the Earth is so inert that that's an inertial frame. Then, with reference to that, we have a rigid body. So again, I draw a potato. And in that potato, we have a center of mass. And again, you know what the definition of the center of mass is, right? We had that up here. That all these static moments, and of course for the third dimension you also have the z part, is 0. So by doing that calculation, you can discover where is the center of mass. Then glued to our body, we have our body fixed reference system. And yeah, sometimes we do use primes as x prime, y prime, or z prime, or sometimes we use capitals here and here small, lowercase and uppercase here, as you like it. But what is important, we give it a name, and we give it this curly b. And that is the body fixed frame. And to denote that it's really fixed to the body, I write this support type of thing. Okay, now what else? Maybe I make the body a bit bigger. I need a little bit more space here. Yep. Then what do? We have, again, in this body, of course, a piece of mass, a small part. And you can draw a circle or a rectangular thing. Anyway, this is a small piece of mass, dmi, again. And how do we find the location of this part? Well, it's like space travel. We first go to the center of mass, and this vector we denote by xc. How do we get at the center of mass? This is the center of mass c. I forget the letter m because I'm lazy. I don't want to write cm, I want to write c. So c is the center of mass. And so we first travel to the center of mass, and then within the body we travel to that position xi. And now I should say, well, it's actually xi prime, right? Because the coordinates are within the system. So that is the way how I can find the location of this point, and the location of this point we call just xi, the vector xi. To summarize, how do we find this point? Well, we say position of xi is you first go to the center of mass of the body, and then from the center of mass you travel to that point within the body. Now, why do we do that? Well, there's one big advantage, that the coordinates of this point in this reference system are always constant. In a rigid body, this x prime doesn't change. So if we write the components expressed in a rigid body, so this is the way how we say, oh, that's not so nice curly b. I'm not so good at writing curly b's. So the components of xi prime, so this is the vector and then expressed in this coordinate system, those are constant. for a rigid body. And therefore we use this notation. Or in other words, my nose will always be in front and above my mouth. If I rotate my head, my nose will still be in front and above my mouth. I mean, that won't change unless I'm a flexible body. And then my nose will change position. But I'm not. I'm a very rigid body. And here too, this guy is a constant factor then within the body. So that is a thing we're going to use. Starting from this kinematic analysis, you say, okay, so the position of point I, of this point mass, is the position of the center of mass plus this relative position of the point mass with respect to the center of mass. How about the speeds? Well, that's thanks to Newton, super simple. X dot I is x dot c plus x dot prime I. Now, what is the speed of this point? You could say, oh, well, it is because the point moves within this reference system, because the mass wanders around in the body, and because the body is rotating. We didn't say that the body is rotating, so we put an omega here. So the body is also rotating with a certain speed. Well, as I said, it has it's a rigid body, so meaning that x dot prime I is only equal to omega cross x dot I. Because the vector in itself, my nose doesn't deform. It stays like that. So we have for our speed expression now omega cross x prime I. So that is our speed expression. And because it's a non-deformable body, we do not have that this thing within the body is changing. Okay, next step, mass, forces mass times acceleration. So we have to look at the forces, right? At the accelerations. So what are the accelerations? Well, again, it's the acceleration of the center of mass plus the angular acceleration times that distance plus, of course, the angular speed times the change, the speed within the body. But we already saw that the speed within the body is this term, so that's omega cross and then again omega cross, so that's a double cross product, so double trouble you could say, x prime I. Okay, let's conclude. The acceleration of a point in the body is the acceleration of the center of mass plus the angular acceleration cross product with the position in the body plus some strange convective term with the omega square. And it's of course in the flat case that's omega square times r, right? That's this. So this is what you omega square times r, and this is like what is it? Phi double dot times r, right? And again, I do like this. Okay, we're almost there. But looking at the clock, I see that I need a break. So let's do the coffee break. Coffee break, don't break the coffee. And see you back in 15 minutes, so that's 2:45.